Welcome students. Let us continue with the discussion on design of synchronous machine. So now we have to learn about the very important topic in the design of synchronous machine, that is short circuit ratio. The short circuit ratio of a synchronous machine is defined as the ratio of the field current required to generate rated voltage on an open circuit to the field current required to circulate rated armature current on short circuit. So if you plot the open circuit characteristics curve and short circuit characteristics curve of an synchronous generator, so at initially when the field current is increases, that is excitation to the synchronous generator, when you increase, then the open circuit voltage, that means rotor of the synchronous generator is kept open and you need to connect a voltmeter in parallel with the any two phases. So if you increase the excitation to the field winding, so then gradually sudden increase in the voltage, open circuit voltage takes place at one particular point, that is rated voltage. When you increase field current, so the output open circuit voltage becomes constant, or it is saturated and it becomes constant. Similarly, if you short circuit the rotor terminals and if you connect a ammeter in series with the any two phases, you are short circuiting the all the three phases of rotor, correct, and connecting a ammeter in the series with the any two phases. Then if you give the excitation to the field winding and you are plotting the, you can take the values of short circuit current for different values of field current. So short circuit ratio is obtained by it is the ratio of field current required to generate rated voltage. For example, the generator is working at 415 volt. What is the field current which is required to build up the rated voltage, that is 415 volt in an open circuit, to the field current required to circulate the rated armature current. So when the short circuit current is nothing but rated current which is applied to the synchronous generator, what is the amount of field current is required to generate the rated current. So that is the ratio of that one is called as a short circuit ratio. The short circuit ratio can be calculated from the open circuit characteristics at rated speed and the short circuit characteristics of a three-phase synchronous machine. So in the synchronous generator laboratory experiment, we have plotted the EMF MMF method. So in that we can plot the open circuit characteristics and short circuit characteristics curve. So this is the short circuit and open circuit characteristics curve of a synchronous generator. All the values are represented in per unit value. So this is x-axis is the field current, per unit values of field current. So F naught is the some value of field current and 1 per unit is the maximum value of field current. So this is the rated value of short circuit current. At rated value of short circuit current, so this is the field current is required. So initially this is the open circuit characteristics curve. So initially the voltage is gradually increasing at rated value of voltage, then it becomes saturation, correct, it becomes constant. Still if you increase the field current, the voltage will become saturation, not suddenly increase when compared to these values. So at one particular value of field current, so this will become rated value. So that is the 1 per unit value. So this is per unit current and per unit voltage. So this is the characteristics curve. So this is the short circuit characteristics curve. So if you increase the excitation, you need to plot the short circuit characteristics curve. So according to the definition, you can write short circuit ratio as the IF for rated open circuit voltage to the IF for rated short circuit current. So this is not if, it is IF. IF for rated open circuit voltage to the IF for rated short circuit current. If you see the figure, so OF naught. So OF naught is the value of IF for rated open circuit voltage and IF for rated short circuit current is OFS. So this is OFS, OF naught divided by OFS. So if you further, it is also equal to CF naught divided by BFS. So CF naught divided by BFS. Fs, correct. So this value OF naught is equal to Cf naught and OFS is equal to Bfs. So if you change the value of Cf naught divided by Bfs is also equal to, if you see the Bfs, then it is also equal to Af naught, correct. So instead of I can write Bfs, in the place of Bfs I can write Af naught, that is it is we can say that Cf naught divided by Af naught, correct. Cf naught divided by Af naught, which is equal to, I can write 1 divided by Af naught divided by Cf naught, just taking the reciprocal. So SCR value we can write it as 1 divided by Af naught divided by Cf naught. So what is that 1 divided by, what is Af naught? Af naught is, this is Af naught, Af naught, correct. So what is Af naught? Af naught is the per unit voltage on open circuit divided by corresponding per unit current on short circuit. So Cf naught is the corresponding per unit current on short circuit. So this is Cf naught. So this is Af naught from the voltage curve. Af naught is plotted from the voltage curve and Cf naught is plotted from the current curve. So 1 divided by per unit voltage on open circuit divided by corresponding per unit on short circuit. So SCR means 1 by XD. So this is the value 1 by XD. So this is the SCR is defined as the reciprocal of synchronous reactance. Synchronous reactance value, that is XD in per unit. For turbo alternators, SCR is normally between 0.5 to 0.7 value, that is short circuit ratio. And for salient pole hydroelectric generators, so SCR value is ranging from 1 to 1.5. So that means the generator which is rotating with high speed or turbo alternator, SCR value is 0.5 to 0.7. And for salient pole hydroelectric generator, SCR value is varying from 1 to 1.5. So the direct axis synchronous reactance XD is defined as the ratio of open circuit voltage for a given field current to the armature short circuit current for the same field current. So the ratio of XD, that is synchronous reactance, is similar to that of short circuit ratio. So it is also defined as the ratio of open circuit voltage for a given field current. For a given field current, what is the value of open circuit voltage and what is the armature short circuit current for the same field current. So that is called as a XD value, that is direct axis reactance. So the definition of short circuit ratio, that graph and simple derivation is very important in the examination point of view. So next we need to learn about the effect of SCR on machine performance. So what is the effect of short circuit ratio on the machine performance? First you need to learn about the voltage regulation. A low value of short circuit ratio means that the synchronous reactance has a large value. So low value of short circuit ratio means it is equal to 1 by XT, that is synchronous reactance has a large value. Synchronous machine with low value of SCR have greater changes in voltage under fluctuations of load. So the synchronous machine with the low value of SCR, that is high value of synchronous reactance, have greater voltage fluctuations, correct, greater voltage fluctuations because reactance is high with respect to the load, that is voltage regulation of the machine is poor. So greater voltage fluctuation means voltage regulation of the machine will be poor. Second point is the stability, how the synchronous machine will be stable under after synchronization. A machine with low value of SCR, that is high value of XD, has lower stability limit as the maximum power output of the machine is inversely proportional to the XD. So the maximum power output of the machine is inversely proportional to the XD value. Therefore the machine with low value of SCR or high value of XD has lower stability limit. Stability limit means, stability means after synchronization how even though there is a disturbance occurs, how strong the synchronous machine will be under synchronism only. So that is a part of stability of the synchronous machine. So if you have the lower value of SCR means the higher value of synchronous reactance. So that will limits the maximum power output of the machine, which is inversely proportional to the XD value. Now third point is the parallel operation. Machines with low value of SCR are difficult to operate in parallel because high value of XD gives small synchronizing power. So ability of the synchronous generator operating in parallel is called as a synchronizing power, correct. So the generator, 2 or 3 generators may be connected in parallel or synchronizing, or the generator which is connected to the electrical grid, correct, electrical grid, that is also called as a synchronizing the powers. synchronizing the generators. So if you the machine is having low value of SCR, that means high value of synchronous reactance. In that case, the machine is difficult to operate in parallel, since the value of XD will be higher, which gives the small synchronizing power. Though this power is responsible for keeping the machine in synchronism. How long the synchronizing power is strong, that much time the generator will be under synchronism. If the synchronizing power is becomes weak, then there will be a problem in the synchronism of the generator. The parallel operation of machines with high value of XT becomes more difficult if they are interconnected through a transmission line. So parallel operation of the machines with high value of synchronous reactance will be very difficult to keep in parallel synchronism, because its stability limit will be become poor. The increase in impedance acts to reduce the synchronizing power, so that they are weakly held in synchronism. So increase in impedance value will be reduces the synchronizing power, therefore they are weakly held in synchronism. The decreased synchronizing power is more likely to lead to disconnection of individual units and shutdown from the operation. So if you have low value of synchronizing power, so that will be leading to the disconnection of two or more generators or individual generators, correct. So that will operate or that will leads to the shutdown of the synchronous machine. So next point we need to learn about the effect of SCR on synchronous generator is short circuit ratio. A small value of SCR indicates smaller value of current under short circuit conditions, giving to large value of synchronous reactance, correct. So according to the definition, SCR value if it is low, then there will be higher value of synchronous reactance will be there. But this is not a problem, because the short circuit current can be limited, and thus the synchronous generators need not be designed with the larger value of synchronous reactance. So that lower value of SCR which leads to the increasing value of synchronous reactance, but lower value of SCR leading to higher value of synchronous reactance is not a big problem, because short circuit current can be limited by using the or it can be limited, and thus the synchronous generator need not be designed with higher value of synchronous reactance to limit the SCR value. So we cannot limit the SCR value by increasing the synchronous reactance. That will lead to the some other problems. So if you have higher value of short circuit current, then that can be limited by some other methods, so that we cannot go for the increasing value of short circuit ratio. So next one is the self excitation. So the machines feeding long transmission lines should not be designed with a smaller value of SCR. So that means higher value of synchronous reactance. So if the machine synchronous generator which is feeding to the long transmission lines, the transmission line is too long, then you cannot design with the low SCR value or higher value of XT. That will leads to the large voltages on open circuit. So there will be large voltages on open circuit produced by self excitation owing to large capacitive current drawn by the transmission line. So the voltage will be higher, large voltages will be there in the open circuit, so that will be leading to the self excitation of large capacitive current drawn by the transmission line. So transmission line will be drawing the large capacitive currents during that period of time. If the transmission line is higher long, then you cannot go for the small value of SCR. You need to have the minimum range of the SCR. Okay, so that is the self excitation. So next we need to go for that is a five points are very important in the examination point of view. So definition of SCR and their effect of performance of SCR on the synchronous machine. So those points are very important. Next topic we need to learn from the design of synchronous generator is length of air gap. What should be the length of air gap to be there in the synchronous generator? The length of air gap greatly influences the performance of synchronous machine. So what are the advantages of having large air gap length? So if you have large air gap length, then you can reduce the armature reactions which occurs in the synchronous generator, and it is also reducing the small value of regulation. So you can achieve the smaller value of voltage regulation if you provide large value of air gap, correct. So that will also lead to the higher value of stability. If you provide a large value of air gap, that synchronous generator will be leading to higher value of stability. Stability limit of the synchronous generator is higher. And fourth point, you need to what advantage of having higher air gap length is a higher synchronizing power, which makes the machine less sensitive to load variations. So if you provide a large air gap, then if even after small disturbances in the load variations or small changes in the load variations also, so the synchronizing power of the machine will be higher. So higher value of synchronizing power, that makes the machine less sensitive under loaded conditions. So load variation, small variation in the load also, the generator will be under synchronizing only. So there is no change in the synchronizing power. And the next advantage is better cooling. If you have large air gap length, so the provision of cooling can be make it better. So better cooling can be provided. So next advantage is low tooth pulsation loss. So there is a large air gap between stator and rotor, between the stator and rotor windings. So you cannot be achieve a magnetic locking of the stator slots and rotor slots. So lower tooth pulsation losses can be achieved, and less noise also we can achieve with respect to large value of synchronous generator. And smaller unbalanced magnetic pull. So the definition of unbalanced magnetic pull or concept of unbalanced magnetic pull we have already learned in the three-phase induction motor. So if you provide a large air gap length, so you can achieve a smaller value of unbalanced magnetic pull. So the disadvantage of large value of air gap is that the required field MMF will increase. So the field MMF, that is flux in the air gap, will be increases, or the amount of magnetic motive force which is should be there in the air gap is increases, which results in large field winding. So you need to provide a large field winding in that case, and the machine becomes costlier. So if you provide a large field winding, means number of copper materials which is required to wound is increases, or the number of turns required will be increases. So the large number of field winding is required, and the machine becomes costlier. Correct. So in salient pole machine, the length of air gap is not constant over the pole arc, but increases from center outwards in order to produce the required flux distribution. So in the salient pole machine, length of air gap is not constant, so it will be varying over the pole arc. If you consider over the pole arc, there will be slightly variation in the length of air gap, but it is increases from center to outwards in order to produce the required flux distribution. For salient pole machines of normal construction and having open type slots, the length of air gap divided by pole pitch is given by 0.01 to 0.015. So for salient pole machines of normal construction and having open type slots, so the ratio of length of air gap to pole pitch, that is Lg by tau, is 0.01 to 0.015. So Lg is the length of air gap at the center of the poles. For synchronous motors designed with maximum output, which is equal to 1.5 times the rated output, So you can achieve length of air gap to pole pitch, that is Lg by tau value is 0.02. So synchronous machine with maximum output, which is equal to 1.5 times the rated output. So in that case, ratio of length of air gap to pole pitch, that is Lg by tau, you can achieve 0.02. So we'll stop here. We'll continue in the next video.